Hey guys, it's Jeff here at Kuroki. Today we're doing a video on an introduction to indexable carbide milling. I brought out a selection of face mills along with a couple of end mills. We've got a couple different mounting styles we're going to go over and some general points on insert selection, what kind of face mill you want to buy, mistakes to avoid, things of that nature. Most of this is going to be larger tooling. We don't have any really small mills here. Our smallest is a 5 horsepower 40 taper. This big Cincinnati is a 50 taper machine, and it originally had a 30 horsepower spindle motor, although we've actually downsized it just due to power constraints. So basically, the first distinction is a face mill versus an end mill. And that comes down to mounting, not necessarily cut depth. People generally think cut depth, but that's not entirely the case. This is a face mill. It mounts on an arbor. It's a shell style. This is an end mill. It has a direct shank that goes into a collet or an end mill holder of some form. That's a difference. This is an end mill, even though it only has one insert high. This is also an end mill. It's just a larger one. This is a Kennametal. It is missing a couple inserts. I didn't bother opening a second pack just to fill it for demonstration purposes. These are often referred to as a corn cob or a porcupine or a pineapple cutter. Their proper name is a helical end mill. You can also get this type of cutter in larger sizes that mounts on an arbor, and they'd be referred to as a helical shell mill. These are basically used if you have to do side milling. You're not going to use these just for surfacing and only be wearing out the tips of the bottommost inserts. If you have a small milling machine, something benchtop, for example, something like this might be all you need. This is a 1-inch indexable end mill. It takes APMT or APKT 1604 inserts, 1-inch cutting diameter. These inserts are a generic style, so you aren't trapped into buying them from one brand. They're cheap, readily available, and they work well. And if you have a machine that won't push more than a 1-inch cutter, this may be just the perfect thing to use as a face mill and just go skimming off 20, 30 thousandths at a time, and it'll work great for you. And very cheap inserts. You can find these for anywhere between about $1.50 and $4 or $5 a piece. Great option. The difference between an APMT and an APKT is in the cutting geometry. This is an APKT. And as you see, they are a full positive. An APMT is flattened off here and has a negative cutting edge. You'll use these for lighter duty machines, lower horsepower, and for softer materials such as aluminum. You'll use an APMT for interrupted cuts, heavier duty work, larger machines. So, for example, if we were cleaning up torch cut parts on this Cincinnati, an APMT would be a better choice. For most of you watching at home, you're going to want to use the APKT inserts. That brings us to the next point. Do you want to have proprietary inserts or generic inserts? There are all kinds of proprietary milling inserts, and we could do multiple videos just covering different options. This is one Kennametal option. This is a small shoulder cutting face mill or shell mill. These are a double-sided with 4 cutting edges, which is nice. You get more cutting points, twice as many as the APMTs. Difference is $3 an insert, $20, $30 an insert. These do perform better, but if you don't need them for your application, you're spending a lot of money on it. And you make one mistake, well, you look at that. That could be more than $100 worth of inserts. Could be a couple $100 worth of inserts, depending on the cutter that you could blow up in one shot. The worst cutter we have for that here is a big Greenleaf indexable slitting saw, and that thing takes over $1,000 worth of inserts to fill it. So you really don't want to be crashing something like that. So things such as those, this 10-inch cutter here is another Kennametal. Most of the tooling I have is Kennametal. Here's another one. This is a Kennametal high feed mill. All of these have proprietary inserts that you can only buy from the company that made the cutter. Generally, you're going to be anywhere between $20 and $50 an insert for the proprietary ones. Whereas you can range anywhere from $1 to maybe $10 or $12 a piece for generic industry standard milling inserts. In general, I would say unless you have an application that the performance difference with a specific proprietary insert is enough to matter, you're better off going with a generic insert. This one here is an 8-inch cutter, and it takes the exact same inserts as this little end mill, just on a larger body. Something like this can be a great option for larger work without getting yourself trapped into something like this that's $800 to fill with inserts. The next thing you want to consider is your cutter geometry, because that impacts a lot about what you can do with them. The kind of three basic types you're going to have are a shoulder cutting end mill or face mill, such as this. I'm going to, again, use this little small one because it's easier to hold up to the camera. These have a straight or relief on the cutting edge, so you can cut up to a shoulder and keep plunging down, cutting deeper, just like you would with a normal solid carbide or high-speed steel end mill. These generally are not as robust of an insert. They generally will have fewer edges per insert, and they generally do not cut quite as well, but they let you get up to a shoulder. On a really big mill like this, it doesn't matter. You could put a butter knife in the spindle and it will chew through it. But on a small machine, it does make a big difference, and these are going to be harder to cut with. The next type is a lead angle face mill. These have a negative lead angle. These are square inserts with 4 cutting edges and set at a very positive rake. These you cannot cut up to a shoulder, but you'll have more cutting edges, and these tend to cut with a lot less horsepower. So if you have a small machine and you're trying to run as large a cutter as possible for just surfacing off the top of parts, something like this is going to be your best bet. You want to look for a lot of positive rake and quite a bit of lead angle. The more lead angle you have, the more of a chip thinning effect you get, and it pushes the cutting forces up into the spindle instead of trying to deflect the cutter sideways. Cutters like this one here, I'll try and turn it around so you can see it. This is not a shoulder cutting one. This just has a very slight negative lead angle. And that is just so that you can get closer to a shoulder but still maintain 4 cutting edges. So those are both lead angle type face mills. And this here is another example. This is one we actually use all the time on our small machine. This takes CNMG lathe inserts and uses the odd corners. So if you do a lot of turning and use a lot of CNMG inserts, this is essentially free face mill inserts. Again, you can't get up to a shoulder, but for a lot of what you do with these, that doesn't matter. And these are going to be your cheapest option to run. I believe some companies make them in larger sizes, but they get quite expensive. This is a generic Chinese one I bought off of eBay for about 150 bucks, and I have absolutely no complaints about it. It's a perfectly well-made, high-quality product. You just search for CNMG face mill on eBay, and they'll pop up. You can also get a version of those that uses CCMT inserts if you have a smaller lathe and smaller milling machine. Another style you'll see here is what's called a button cutter. These use round or button inserts. These obviously cannot cut to a shoulder. These have 2 uses. One, on more manual machines and conventional use, it's for rough, nasty work. Cast parts, heavy hot rolled scale, cleaning up forgings, cutting down torch slag, things of that nature. They're a very robust insert and tend to hold up to that better than most will. You can also take shallow depth of cuts at a really high feed rate and basically treat these like you would a high feed mill using a chip thinning effect. Where these are a lot more commonly used and arguably a lot more useful is on CNC milling machines, where you'll use them for profiling cycles, roughing out mold cavities, things of that nature. These aren't that useful on manual machines. They also are quite hard on the machine. They have high cutting forces. Again, something like the Cincinnati, it doesn't matter, but if you have a small mill, like even something Bridgeport size, you're probably going to be disappointed with one of these. The last option here is a dedicated high feed cutter. You see the angle this sits at. These are only capable of taking a very shallow depth of cut. This cutter will only take up to 90 thousandths of an inch at its maximum cut. On the other hand, you can feed these incredibly fast. You can actually cut with the table in rapid traverse on this Cincinnati. These are something where if you have big surfaces you want to skim down quickly and don't have much metal to remove, they can work really well on manual machines. They also can have pretty high metal removal rates if you just step over and keep knocking off 90 thou at a time, feeding really fast. Again, they are something that's more commonly used on CNC milling machines. Just because, again, you can alter your tool path and do all sorts of other things with them that you just can't do on a manual milling machine. They also can have their place if you get a really small, like 1.5 inch high feed cutter. They can work really well on smaller and lighter duty milling machines too, because again, like I was talking about with the 45-degree lead angle, they push all your cutting forces up into the spindle. And that tends to be a lot less prone to chattering having axial loading versus radial loading on your cutter. This is another little button cutter. I don't actually have any inserts for this one, but it was in the drawer, so I figured I'd pull it out and show you. The next point is mounting. Again, in smaller sizes, these are just going to have a round shank, like a normal end mill, and you put these in a collet or a Weldon holder on a CNC if you have that kind of tool, and you can use shrink fit holders. That's common on small cutters. Their 2-inch shank does exist, but it's uncommon. Usually when you start getting above about 1.5 inch or 2-inch cutter, where you'd be more than 1.5 inch shank, you're going to switch over to being a shell type. And that would be things of this nature. They have a drive key in the back, they have a pilot diameter in the body, and they have a bolt that holds the cutter onto an arbor. This way you can have different cutting heads and just swap them out on the same arbor, and not always, but usually most cutters in a given size will have the same back mount, so they all interchange in the same arbor. That's going to be your standard from roughly 2-inch to 6-inch cutters are going to be mounted that way. This is a 6-inch, and it's on a arbor as well. This is a Weldon quick change arbor, but it's the same idea. It just has the bolt in through the face. When you get above 6-inch, you have two options. You can continue to mount them the same way. This is a 10-inch cutter, and you see it has just a big 50 taper arbor on the back that goes in the spindle. That's still valid. The problem you start running into is there's more sticking out from the spindle and there's more overhang from the side of the arbor. And I really don't know that I'd want to push anything bigger than a 10-inch this way. You can get face mills up to 12, 14, 16-inch diameters. And when you get into the larger ones, generally any face mill 8-inch or larger will be designed to be bolted directly to the spindle nose. There's two ways this can be done. Either they still just maintain a regular hole in the back, and you have to get a guide plug that goes in your spindle. This is basically a 50 taper shank that just has a pilot diameter here that fits inside the cutter. No drive keys, and it doesn't stick out past the spindle nose. You'll slide the cutter up in place onto the spindle, And then in the case of a 50 taper, you'll use 4 5/8 inch by 1.5 inch cap screws, torqued to 130 foot-pounds, and physically bolt the cutter directly onto the spindle nose. This is a very rigid way of mounting, and it gets rid of both the excessive stick out from the spindle, and you have as much contact area as possible because you're bolted directly to the surface of a milling spindle as opposed to having to transfer everything through an arbor. The other style, which I don't have a cutter to show you unfortunately, will have a pocket cut in the back. This will be more common on larger mills. Things like this 10-inch is where you'll start seeing it sometimes, and a lot of the larger ones you'll see it almost universally. And that pocket actually fits around the outside of the spindle nose, so you don't need the plug inside of it anymore. You can instead directly fit it over the outside of the spindle and bolt it straight on. And again, those are just to give you a lot better rigidity for large, heavy-duty cutting. Something like this cutter here, provided you had enough spindle power, you could be putting 60 to 75 horsepower through that cutter, taking off a big, heavy cut. So like everything, there's trade-offs. And a lot of this information probably isn't all that relevant to most of you watching, but I thought it might be interesting to go over some of the larger stuff as well. Like I said, for your average home shop, or smaller job shop for that matter, you're probably going to want basically something like these two. You're going to want something that'll cut to a shoulder and something that'll have lower cutting forces and you can work faster with. And you're probably going to get away with these two. On a Bridgeport size milling machine, they'll usually run pretty happily up to about a 2-inch cutter. They can be pushed to a 3-inch. The 40 taper Bridgeport styles will run a 3-inch quite happily and can be pushed to a 4-inch. Any bigger than that, you're really going to be better off using a big 50 taper mill. And if you don't have one of those, just use a smaller cutter and step over more. You're going to end up having a higher metal removal rate, taking heavier cuts and pushing faster with a smaller cutter than taking really shallow cuts and feeding at a crawl to keep your big cutter from chattering. And the other big takeaway I would make from this video is try to use tooling that takes generic inserts. The proprietary stuff certainly has its place. And again, if you're like an aerospace shop or a big mold shop or any kind of high volume production running CNC machines, it makes sense. There's a reason that stuff is dominant on the market. But for most of us, you're not doing enough volume of metal removal to the point where the $30 inserts are outperforming the $4 inserts by enough of a margin to be worth the cost of it. The cheap tooling has really come a long way in recent years, and I've been pleasantly surprised with most of it that we've used. The milling stuff especially seems to generally do quite well. Anyways, I hope all you found that helpful. If anyone has any more questions or comments, please feel free to leave them in the comments down below. We are going to do some more milling videos in the future. We're going to do some cutting demonstrations. We're going to show how to do some basic setups. We'll go over end mills and boring heads and other things of that nature. And if any of you know anyone or any groups that may find this content helpful, please do feel free to share the videos. Every little bit of exposure helps us grow the channel and helps us make more videos. Thanks for watching, and I hope you all have a good day.